Episode 7. Episode 6 laid out 4 questions and then stopped short on one of them. It named 4 mechanisms under how and said the systems belonged here. This is here. The whole episode is the how axis taken seriously, which in practice means automated search, a machine proposing changes to an agent and something else deciding whether they were good. And I want to put the uncomfortable part first rather than last, because it shapes everything that follows. The thing deciding whether a change was good is usually the same thing the search is optimizing against. That is not a flaw in any of these methods. It is the shape of the problem. Start with a picture you will recognize if you have ever done this. An agent tunes its own prompt over 12 revisions, and you record 2 scores at every step. The validation score, the one the search can see, rises the whole way. The held-out test score peaks at revision 4 and then falls for 8 straight revisions. Nothing malfunctioned here. No component failed. The search did exactly what it was told, which was to maximize the number it was shown. Everything in this episode is downstream of that one sentence, and so is a good deal of episode 9. I have shown this plot to teams who then went looking for the bug. 3 objectives. Describe automated optimization as search over a space defined by 3 choices. Explain what a textual gradient is and, more usefully, where the gradient analogy stops holding, because it stops earlier than the name suggests. And decide when automated search beats hand design, using evaluation cost as the deciding variable rather than taste. One boundary before we start. In this episode the optimizer and the thing being optimized are separate objects. An agent that rewrites its own code is episode 8, and that difference is not a matter of degree. Slide 15 is about exactly where the line falls. The 3 choices arrive next, and they are the vocabulary for the rest of the episode. Here is the frame, and it is ours rather than any paper's. Every automated optimization method is defined by 3 choices. Representation, what is being optimized. Operator set, the legal moves, what the search is allowed to do to that representation. And evaluator, how a candidate gets scored. Every method in this episode is one specific triple of those 3. The claim worth testing as we go is stronger than a classification, though. The triple predicts the cost and it predicts the failure mode, which means you can read both off a design before you look at a single experiment. Hold me to that by slide 22. 3 choices, and the rest of this episode is 4 worked examples of reading them. First choice, representation. There is a ladder here. A prompt string is cheapest to change, cheapest to evaluate, and the least expressive thing you can optimize. A component graph, nodes and edges over model calls, is more expressive, and now a candidate is a structure rather than a string, which changes what an operator even means. And workflow code is the most expressive of the 3. The usual rule is that each rung up is harder to evaluate as well as more expressive. The top rung breaks that rule, and the reason it breaks it is one of the more useful things in this episode. Slide 18. Notice that the ladder is about the candidate, not about the agent being built. Second choice, the operator set. Edit, change a component in place. Insert, add one that was not there. Swap, replace a component with another from an inventory. Refactor, restructure without changing what the workflow computes. This is the choice that papers leave implicit, and it is the one that decides everything, because the operator set defines what is reachable. 2 methods with the same representation are frequently not searching the same space at all. Which has a consequence people skip. Their results are not comparable even when their benchmarks are identical. Same benchmark, different reachable set, different problem. Write your operator set down before you start. Nobody does, and it is free. Third choice, the evaluator. A metric, computable, fast, and measuring a proxy for what you actually want. A judge, a model scoring another model's output, flexible and unverifiable. Or an executed test, where the candidate is run and the result is a fact rather than an opinion. You have seen this before, it is episode 6 error signal ladder, applied to a search instead of to a single refinement loop. And of the three choices, this is the one that ends up mattering most. The cost model later in this episode is driven entirely by this column, and not by the other two. Cheap and wrong beats expensive and wrong, but only one of those is worth optimizing against. The first method treats feedback as a gradient. Natural language critique is propagated backwards through a chain of components, and each component receives a critique of its own contribution. The API is deliberately pytorch-shaped, variables, gradients, an optimizer that consumes them. Two modes are worth separating. Instance optimization refines the solution to a single problem at test time. Prompt optimization looks for a prompt that helps across instances, and that mode implements stochastic minibatch gradient descent, which tells you how seriously the analogy is meant. Reported, GPT-4o on Google Proof QA from 51 to 55%, and 20% relative on LeetCodeHard. The word gradient in that name is doing more work than it can carry, which is the next two slides. So how far does the analogy actually run? Four things carry over honestly. Composition, a system of components can be traversed backwards and each one told what it contributed. A chain rule shape, feedback at the output becomes feedback at every interior node. Iteration towards a target with an optimizer object that consumes feedback and produces an update. And batching, mini-batches genuinely apply here. What this is, stated plainly, is an architecture borrowed from automatic differentiation rather than a mathematics. That is not a criticism, borrowing the architecture is what makes compound systems optimizable at all. It does mean the guarantees do not come with it. Borrowed architectures are how most engineering progress happens, so this is a compliment. Here is one pass. For components, a forward pass, and a loss arriving at the output. Feedback then propagates backwards, and this is the part that repays attention. Each component receives a critique of its own contribution, not a critique of the whole system. That decomposition is the entire trick. Watch what the third component receives. It is a sentence. It is not a number, and it is not unique. A different critic would have produced a different sentence, equally valid, pointing somewhere else. Then the optimizer rewrites each variable and the forward pass runs again, and that is one step. One step, and already 4 separate judgments have been made by a critic nobody audited. And here is where it stops, in 4 places. No linearity, a gradient is a local linear approximation, and a critique is not local, not linear, and not an approximation of anything. No step size, you cannot take a small step in the direction of a sentence, so every update is whatever size the rewrite happened to be. No convergence guarantee, there is no descent lemma, so iteration can oscillate and can move backwards while the score moves forwards. And no uniqueness, which is the deep one. In ordinary optimization the gradient exists whether or not you compute it well. Here there is nothing underneath the estimate. Any one of the 4 would be disqualifying in numerical optimization. Here they are the working conditions. One connection to close before moving on. Episode 4 meta-textual gradient inside a memory method, contrastive feedback used to induce guidelines for what a good memory entry should look like. That slide pointed forward to here for the concept itself, and this is where it comes from. Notice the direction of travel, because it is the interesting part. An optimization idea entered the memory literature, rather than the other way round. Which is worth noticing about a field this young. These two halves of the series are not two literatures politely coexisting. One of them is already importing from the other. Watch for that pattern elsewhere, borrowing usually runs from the older field to the younger one. The second method searches over agent designs rather than over text. A meta-agent programs new agents in code, evaluates them, and adds them to an ever-growing archive, and the archive conditions the next proposal, so the search is not memoryless. Each round starts from everything discovered so far. Because agents are defined in code, and most programming languages are Turing complete, the space in principle contains any agentic system at all. Reported, 13.6 F1 points on reading comprehension, 14.4% on mathematics, 25.9 on GSM-8K. And the discovered agents transfer, across domains and across models, which is the claim I find hardest to dismiss. And here is something the optimization framing hides. That archive is a memory store, so read it through episode 2. Right, every evaluated design is added. Index, by its performance and its description. Retrieve, the archive is read back to condition the next proposal. Update, absent, a design in the archive is never revised. Forget, absent, it grows monotonically. Consolidate, absent, similar designs are not merged. 3 of 6. Which puts this search in exactly the position of 3 of the 4 architectures from episode 3, no revision path, and a store that only grows. The archive is doing memory's job and inheriting memory's problems. Which is a good argument for reading optimization papers with the memory chapter open beside them. One distinction, and it is the boundary of this whole episode. Here, the meta-agent designs other agents. It writes their code, evaluates them, files them. Its own code is not in the search space. Next episode, the agent rewrites its own code, the searcher and the searched are the same object, and the archive becomes an archive of itself. Both have archives, and that resemblance is exactly why the distinction has to be stated rather than assumed. In the 3-choice language, next episode all 3 choices collapse onto one subject. The representation is the agent's own code, the operators are edits it writes, and the evaluator is one it selects. So state its triple. Representation, code for a whole agent. Operator set, propose a new design from building blocks, conditioned on the archive. Evaluator, a benchmark score. Now do what slide 4 promised and read the consequences off the triple rather than off the results section. Cost reads off the evaluator, 1 full benchmark run per candidate, and each candidate is an entire agent. Failure mode reads off the operator set, proposals are conditioned on an archive that never forgets, so whatever is discovered early steers everything that comes after it. Neither of those required an experiment to see. 2 predictions, both made from 3 lines of description, both checkable against the paper. The third method searches over workflows expressed as code. Nodes joined by code-based edges, so conditions, dependencies and logical flow are all code rather than configuration. The search is Monte Carlo tree search over an operator set, with a soft mixed probability selection rule. Modifications are proposed by a model, the feedback guiding them is execution feedback, and the tree itself carries the accumulated experience. 6 benchmarks, and an average improvement of 5.7% over state-of-the-art baselines. But the number I would put on a slide in a budget meeting is the second one, smaller models beating GPT-4o on specific tasks at 4.5% of its inference cost. Now the point slide 5 deferred. Expressiveness usually costs you evaluability, a richer representation means a harder judgment about whether a candidate is any good. Code is the exception, because code runs. The evaluator can be an execution rather than an opinion. So moving up to the most expressive representation moves the evaluator up episode 6 ladder rather than down it, from a judge to an executed test. I think that is the single most useful structural fact in this episode. It explains why the domains where automated search works are exactly the domains where correctness is executable, and it tells you where it will not work yet. It also explains why prompt optimization and workflow search feel like different activities. They are. Here is a search running. On the left a workflow graph mutating under the operator set, a node edited, a node inserted, a branch swapped. On the right the search tree growing, and beneath it the score curve. 2 things to watch. First, watch the tree rather than the graph, because most of the search is spent on branches that get abandoned, and that is not waste, it is what search is. Second, watch the score axis. Every single point on that curve cost 1 full execution of the entire workflow, and that is the fact the next slide is about. Abandoned branches are not failure. Paying for them is the entry fee. Which gives the most practical claim in this episode. Tree search does not reduce the number of evaluations you need. It decides which ones to spend. Every node expanded costs one full evaluation of a candidate. A better search policy buys you a better chosen sequence of evaluations, not fewer of them per unit of improvement. So the total bill is set by the evaluator, and the search algorithm only decides how well that bill is spent. It follows that a cheap evaluator is worth more to you than a clever search. That ordering surprises people, and I am confident it is the right ordering. If you remember one operational claim from this episode, make it this one. It's triple. Representation, executable workflow code. Operator set, a fixed inventory applied to nodes of the graph. Evaluator, an executed run against a task set. Read the consequences of it again. Cost comes from the evaluator, an execution per candidate, expensive per unit, but a fact rather than an opinion. And the failure mode comes from the evaluator as well, which is the part worth carrying home. Whatever the task set fails to cover, the search is free to break. It is not merely permitted to break it, it is rewarded for breaking it whenever that buys a point on what is covered. Rewarded for breaking it, not merely permitted to, that distinction matters when you write the task set. All three, side by side. And one thing this table deliberately does not have, a scores column. These three report on different benchmarks under different conditions, and putting their headline numbers in one row would invite a comparison that none of them support. Each method's numbers are on its own slide with its own conditions, which is where they belong. What the table does show is the payoff of slide 4. Read down the evaluator row and then the cost driver row. The evaluator predicts the cost. The representation does not. And the last row is what each method is structurally blind to. The blindness row is the one to photograph and take to your next design review. So here is the cost model, and it is one line. Search cost equals candidates times evaluation cost. Two axes, and a budget line drawn across the plane, everything under the line you can afford, everything above it you cannot. Watch the affordable region as the evaluation cost rises. It does not shrink gently, it collapses towards the origin, because the relationship is multiplicative. Which gives the sentence I would want you to leave with. A tenfold cheaper evaluator does not make your search 10% better. It makes 10 times as much search affordable, and search is the thing that gets better with volume. Multiplicative relationships punish you faster than people expect, and reward you faster too. And what that implies if you do not have a large budget, which is most people. If your evaluator is a model call, the budget line is low and it binds immediately, so hand design, and spend the effort you would have spent on search on building a cheaper evaluator instead. If your evaluator is an executed test, the budget line is high and hand design is the waste, because the machine can try 100 candidates for the price of your afternoon. The top rung of episode 6's ladder is what makes search payable. And there is an existence proof, a smaller model, searched, beating a frontier model on specific tasks at 4.5% of its inference cost. Lab 7. Take one prompt of your own and write down its operator set explicitly, the 4 moves you will allow yourself, and no others, because the discipline is the point. Then define 2 evaluators, the one you will optimize against, and one you will not look at until the end. Then run 10 iterations by hand and record both curves. 30 lines and an afternoon. The second curve is the whole lab. If it never diverges, you have learned something useful about your evaluator. If it diverges, you have just reproduced slide 2 with your own hands, on your own system. Do not skip the second evaluator. It is the only part of the lab that can surprise you. 5 takeaways. 3 choices define every search, representation, operator set, evaluator, and every method is one triple. The triple predicts cost and failure mode before any experiment, cost comes from the evaluator, and blindness comes from whatever the evaluator does not cover. A textual gradient borrows the architecture of automatic differentiation but not its guarantees: no linearity, no step size, no convergence, no uniqueness. Code is the representation that breaks the trade between expressiveness and evaluability, because code runs. And a cheap evaluator is worth more than a clever search. Next episode, all three choices collapse onto one subject. And that collapse is the whole subject of the next episode.